number system, and we talk about is our number system. So, any questions regarding our following project and the final project? Okay. Okay, let's see last time. And can somebody tell me, people are asking questions, can somebody tell me what is the sampling theorem? Without looking at your
in order to basically get a good, take good data, your sampling frequency needs to be twice, at least twice that of the signal frequency.
Right? It's close. The sampling theorem states that the sampling, if you want to reconstruct your signal, the original signal, the sampling frequency must be greater than or equal to 2 times of the maximum of your original signal, maximum frequency of the original signal. And then we talk about hexadecimal binary hex. It is the auto, the base, and I will teach you how to convert from one system to another. And so this one will be appearing in our exam number 1 on testing conversion and how to do this conversion. Be very, very careful. And then we talk about 2 important concepts and that actually you have never ever heard of before you take this course. One is called once complement. Once complement means that you just change from 0 to 1 and also from 1 to 0. This once complement is easy to understand. It's once complement, right? So outside binary number, and you change 1 to 0 to 1 and 1 0 becomes the switch. The second concept is called the two's complement. And two's complement for the signed numbers. I told you the computers look very, very smart, but it is not as smart as well. Right? So they just only can do the addition, cannot do the subtraction either. So if you want to do the subtraction, and you must change the number, change the negative n. For example, look here. Okay, so this is a number, is a positive number, and this NC is this guy's whose complement. Right? So if you want to calculate, for example, so NC is 2n, and 2 is the number, n is how many digits you have. And for this example, 0, 1, 1. So this is 0, and the heaviest one, heaviest bit is 0 means that this guy is positive. So 0, 1, 1. The decimal, this is the equals the decimal 3, number 3. And you want to change this one to 2 power 3, okay? So using this equation, 2 power 3 is equals, in binary is 1, 0, 0, 0. A binary is the original one. Original one is 3. And so this is minus 0, 1, 1. See? 1, 0, 0 minus 0, 1, 1. So you get 1, 0, 1. This 1, 0, 1 equals minus 3 for the decimal. That sounds right? If you want to do something, some one number, for example, is x minus 3, and you need to do what you need to do. You need to get minus 3 first. Minus 3 actually is the 2's complement of positive 3. And then you put this is x, whatever number you have, x, put them together and add them together. Right? That's the reason I say the computers, they are not as smart as we are. So note that here is an extra negative number and then a positive number, which this is a signed number. Here is the example. So here is one addition that the teaching what I just told you. It is performed on signed number. The numbers are added regardless of the sign. Subtraction. Yes, subtraction involves adding 2's complement of the subtraction. Understand? If you want minus 3. The computer does not know how to minus 3. What you need to do? You need to get this is the 3's the 2's complement minus 3. And then you put this x with this minus 3. to do the addition, we send them some function. So here is one example. This example says that we want to calculate 4, right? 4 minus 6. Don't tell me you can get it. I managed very quickly, right? So, but for system, for the computer, how to do it? So you can get these 4, okay? 4 this is decimal number 4. Decimal number 4, you have this is 1, 0, 0. For other all are 0. You need to calculate. This is minus 6. So this is minus 6. And how to calculate? How to conduct perform this is subcalculation? And 4 minus 6. Right? At that time, you need to get this number 6. So get this number minus 6 first. And how to do it? So this is 6. Let's see. This is 6. This is 6. It can be changed into the binary, and binary number will be 0, 0, 0, 0. So this is first of all, this is X number, and then we have 0, 1, 1, 0. So these are the states. These are states. This is my binary number for states. Are you following me, guys? Okay, now I want to calculate this is minor states. Convert to minor states. How to do that? Minor states equals 2n minus 6. Okay? So how to do that? I will go to 2's complement. So the 2n and n equals here, n equals 8. So I will have 1, 0, 0, 0, 0. This is a 4. 0, 0, 0, 0. This is another 4. Right? Why I include them into 4? Because the text number. So this is my 2n. And then minus 6, minus 6, I use this equation. I just put it here. I just put it 0, 0, 0, 0. Here, 0, 1, 1, 0. And then minus. And you will see what number I will get. I will get. So 0 minus 0 is 0. So this 0 minus 1. So I need borrow 1, right? So but this borrow 1, that means 0 minus 1 will be 1. So this one is borrow, and so this one becomes 1. That means I borrow another one from here. Is 1 minus 1 is 0. Right? And this one is borrow 1 minus 1. And this borrow. And I will have 1, 1, 1, 1. So this will be my minus 6. And this guy's 2 complement. So because and you follow it, I will from the here. So this 0 cannot do minus 1, right? You need to follow 1 from the higher bit. Right? You follow 1, and that means you follow 1 and 1, 0 minus this 1, which will equal to 1. But here you followed. Just as if I have money, I have $1, after you borrow me, I will have 0. So because they come negative, that's going to have to borrow. Yes, you need to borrow. It's very similar to our decimal one. Right? So this is 0 cannot minus 1. And you need to borrow 1. If you borrow 1, that means so these ones, if you borrow 1 and 0 minus 1 equals 1, but you need to borrow. Okay? So because you borrow 1, this one becomes 1, and I will borrow 8, but you need to borrow this, borrow from here continuously. And we will borrow this 1 becomes 0. So this will be my minus 6. Okay? So as I said, so this one must be performed using 4 minus plus minus 6. And then I use single 4. Big 4 is this is my 4. 4 is 0, 0, 0, 0. My first 4 bits and 0, 1, 0, 0. Minus 6. This is my minus 6, right? minus 6 is what I just got, and 1 1 1 1 1 0 1 0. I'm just put them together, plus them together. Because 0 0 0 0 1 1 1 0 1 1 1 1 1 1. So here, this one is minus 2. So this one is minus 2. Right? How together is minus 2? And 2, you can use 2 and you use the same equation, and you can use this equation, and this one minus 2, and you can minus this is the number 2, okay? And you will get this is negative 2. And that is equal to 2. The same thing, and the same thing for this, the same thing for this one. I'm going to show you. Any questions before? Let me take picture and I can post this one online. Who gets that in 2 minutes? 2 minutes, right? Good. So what I want to show you is that 4 minus something, a minus b, and you cannot do a minus b directly. You need to calculate the negative b. I will put a and negative b together, add them together. And I'm going to erase this one and show you the second part, the second example. And for second one is the same. Okay, you need to change the 57. Right? It's the 57. We can have the 57, and you can convert this one. Right? And then if you convert this one to band rate, it will be 0 0 1 1, and it's 4 digits, 4 bits, and 1 0 0 1. So this is corresponding to this is the D. So this is the B binary. So I want to calculate the 57 minus on the 43. And you get minus 43. That is the 2's complement of 43. The 43, let's calculate the 43, okay? Let's convert on the 43 to this is the binary. How to do that, guys? And it is divided by 2, right? And we will get 21, and the remainder will be 1, right? And then we continue to calculate this. Divide this one by 2, and we will have 10. And the remainder will be 1 also. And then divide by 2 again, and we will have 5. And this time, and the remainder is 0. So great. Okay, we'll continue the 2, and this is 2, and we have 1. So here this is a 2, and we have 1, 0. So this is 0. And then we have 2, 0, 1, 1. Right? And 0, 1, 0, 1, 1. Can someone tell me what is 43? 1, 0. 0, 1, 0, 1, 0, 0. 1, 0, 1, 0. That's the reverse. Reverse. 1, 0, 1, 0, 1. Okay, it will be 1, 0. 1, 0. These are 6 digits. I see. 1, 0, 1, 0, 1, 1. 1, 1. So here is using the T. Questions so far? So this is my positive 43. And how can I calculate my negative 43? My negative 43 equals 2 power A R8 minus R43. Right? So for here, on the 2 powers 8, the 8 is 1, 0, 0, 0, 0, is a 4, 0, 0, 0, 0, and this is the 74. So this is by 2. And 43 is this. And minus. And this is my 43. I just copy here. 0, 0, 1, 0, 1, 0, 1, 1. And then you can do it. Right? And then you can, what you will get, this is 1. You follow this here is 1, 0, follow, 1, follow, for this one, follow, you can follow this one. Because 0, while having follow, become 1, 0. And so this is 1, and this is 0, and 1, 1, 0. I think that is. So finally, so this is my number. This is my negative 43. Okay, so minus 57 minus 43 will be 57 plus minus 43. So you put this one together with this, and you will get the final results. I want you to practice. So in our first exam, I will give you another number and let you guys to calculate for the other side. Okay. Then we talk about any questions so far? Okay. Okay, so then we talk about the next topic, the digital devices. Digital devices. So here are 2 different kinds of digital devices. First one is the combination of logic device, and second one is the sequential logic device. Combination of logic device, the difference between these 2 guys is that for first set of these devices, and their output is only dependent on the inputs at that instant. Right? However, sequential logic device and the output of this kind of devices not just dependent upon the current status of the input, but also the history of the input. That's the reason called sequential. Can I sense everyone? Okay, let me repeat, okay? The output depends purely on the input values to the device at that instant. For the previous status of the input data does not have any influence on the output. Here, sequential, the output depends on the sequencing history, that history or timing of the input signal. So these are 2 different kinds. And for this, the first set we have AND or and not nor gates. And so this one we will not talk about this one. We only focus on the combination of logic devices. So for the second one, the flip-flops and latches. So first, gate we call the gate. Okay, the gate, just like the gate we enter is the gate. So this is the gate. The first one is the invert. Invert means the object of your input. So here in the symbol, and within the triangle, we have here we have the empty in the circle here. So this is the symbol of invert or not a gate. Not a gate means that we have one input, right? And the output C equals the object of your input. The time history is this. Right? Whenever your input is 1, is 0, your output is 1. And whenever, I'm sorry. So whenever this is A is 0 and C is 1. Whenever A is 1 and C equals 0. Opposite. Right? So in the time history, and so I'll just give you this timing history we call the timing diagram. And timing diagram you can see this is the time t, okay, and for simplicity, I just maybe just eliminate this. But in this direction, it's the time. It's time and how this A is changing and what the time goes. And so you can see, I have A, I can just plot C here. So in our first exam, I'm going to show you guys if I put into some gates and I give you the time diagram, time history of the inputs. I want you to draw the time history of the outputs, which will be able to do that, right? So you remember, for this here, this x-axis, horizontal axis is time. This is how the A changes with the time. And so here is how the C changes with time. And it is obvious. This high is low. And this low and this high. Okay, right? So we should know that binary. Binary means we have 1, 0, and sometimes we call high, low, sometimes we call on, off, this kind of thing. So second gate is AND. So this AND we have two input values. This AND AB are input and C is output. And the gate, the signal. This AND the signal. And you can see logic is 1A, okay? And 1A, A and B, when this is 0, 0, and C will be 0. This is AND. Okay, you know AND, right? And means that if any value of input equals 0, the final result will be 0. But you can see this is a truth table. I will call this a truth table. I will call this as a timing history, timing diagram. Timing diagram. Truth table, timing diagram. You can see 0, 0, the C is 0, 0, 1, the C is 0, 1, 0, and 0. Even whenever there is 1, 0 for the input, and your output will be 0. And the output can only be 1 if only if this is these two values, all the inputs, they are 1. Right, so this is called AND gate. And we have truth table, and we also have the timing diagram. And C equals A dot B. Next one is a combination of these previous two gates, and not AND, these two. So you can see, if this one is not empty circle, it will be AND gate. But if this circle is empty circle, so this is a combination of AND gate and NOT gate. You can see it's just opposite, okay? And for the AND gate, only if your inputs are 1, and you will get 1. But there is a NOT there, okay? NOT there, just obvious. So for this one, as long as there is one input equals 1, 0, one input equals 1, 0. So this output will be 1. And when output equals 0, only if, and these two guys are equal to 1. The reason is that so this gate is a combination of AND gate and this is a NOT gate. So here the truth table is given here. And then we talk about this OR. OR is very good. It's just like a move, right? So R, it means that as long as one input is 1 and your output will be 1. Right? So here you can see, as long as one input equals 1 and your output will be 1. And if this guy equals 0, only if both A and B are 0. So they call it OR. OR is the signal. And C equals A plus B. And then we talk about this NOT. This NOT is a combination of NOT and this is OR. So we can know the truth table. We can imagine the truth table. Okay? So as I said, for the OR gate, only if as long as one input equals 1, your output will be 1. But here, because this is all not 0, right? Just operate. And so XOR is special, and so you need to pay more attention to this. XOR, it says that it is R, right? It's exclusive R. It is R. It has that is a moon, like a moon. But this is another symbol, another additional is a curve here. And what this guy says, it says that the results can only be 1 only if and your inputs are different. Right, guys? So it says that only if your 2 inputs are different, your output will be 1, will be high. And if these 2 inputs are the same, your output will be low, 0. To know that, okay? 1 means high, 0 means low. High, 1, 0, high, low, 2 ports, open and close. To know that, right? The 2, this is a 2-value system. So XOR. So, and then logic gate is a buffer. And this buffer is the same, the logic is the same. Right? In the logically, the input and output are always same. But what happens? And there is the amplifier. Okay, guys? Because, for example, you want to drive something, some of these actuators, but this is signal is not that powerful. You need to have this buffer. Buffer means that it does not change logic value, but the power will change. Increase the input on output signal current. C equals logically, and C equals A. And then we talk about the Boolean algebra fundamental laws. The Boolean algebra. And you have learned the linear algebra, right? The Boolean algebra handles the binary system. Boolean, we have this is any number plus 0 equals is a number. Okay, each number only 2 possibilities. One is 1, one is 0. Make sense? The Boolean, as I said, Boolean algebra handles the binary things. Binary things means that only 2 values. So this A here, I just give you a number. I give you a value. This guy can be 1, can be 1, and can be 0. So any signal plus 0 is the signal itself. Any signal plus 1 is high. All right? It's understandable, right? Any signal plus its own is the same, logically the same. If this guy is high, this guy will be high also, and the results will be high. Otherwise, 0, 0, and this guy will be 0. I mean, any number plus this guy's output will always be 1. You agree? Yeah, it's understandable. If this is 1, not A will be 0. 1 plus 0 equals 1. If this guy is 0, not A become 1, and the result will be 1. This is understandable. So it's R, and if and, okay? And no matter what this value is, when you end this one with 0, and you get 0. Right? But no matter what the value this guy is, if you end A with 1, and you get this A, same thing. And A is there. If you did 1, it's 1. If you did 0, it's 0. So A, not A, always 0. Okay, that means if this 1, not A will be 1, 0, right? 1 and 0 equals 0. If this is 1 and 0, not A is 1, 0, 1 equals 0. Okay. Wait, for this one, not A If not again, then we stop. I just want to broaden your further knowledge, but I will not test your understanding. If you want, I can test you. Okay, there are several laws here. Cumulative, you can change it. You can switch the order. A plus B equals B plus A and is R. Okay, A R B equals B R A. A and B equals B and A. So association. So these are parentheses plus C, R C. I need to just scramble them together. And also is A and B and C equals A. And I'm going to put C together first. And then distributed. So A parentheses equals A and B plus A and C. A plus B and C equals A plus B multiplied by A plus C. So this guy is kind of new and you pay attention to it. Understand? I just want to give you new knowledge. I will not test your understanding of this in our exam. So De Morgan's law. The De Morgan's law, this is De Morgan's law is a very, very important law in the linear the Pulling algebra. So what it says, so plus stands for the R. Let's start plus stands for R. The bar on the top is not. Okay. This one equals A naught and B naught and C. You can see if this I have this one, I change the R to the naught to the N. So here and bar I change it to the R. Right? This is De Morgan's law. And then, so you can use De Morgan's law to simplify the case. And so here is a case. And so this case will be much simpler, right? So how to do that? And instead just, for example, C equals A and B bar and B. And you can use this De Morgan's law. And so you put up this guy can be extended as this one, and then you just use association with this law, and you can see equals A bar, not A, and B. So this one, and so this one is okay, but this one will be simpler. The timing diagram. I'll show the timing diagram. So here is the timing diagram. I think I will give you gauge. I will give you call the one input in changing and call another input changing. And then I ask you to draw the C, to draw the output. You should be able to do that, right? Okay, so the key is that, and you know, here is the time, and this is the time, and you just want this distance, and to do the logic operation, whether this is and or X or R or whatever. Based on the bit, and we just draw the time diagram. Any questions regarding our number system?